you're ready.
Good. Thanks, everybody. Today, what I'm going to talk about is, the title, I think, is Electron-Phonon Interactions in Moiré Graphene, which is like a very general topic, and you will see that I will not cover everything about it. Instead, what I will do first, because I think this is supposed to be a link between what you have in classes and then research, I will start with a very broad review of electron-phonon interactions in Jellium Model, and then link it to one of the works that we've done related to electron-phonon interactions in Moiré Graphene, and how I hope it will be useful to fully grasp what we've done. So the first thing, let's talk about electron-phonon interaction. Jellium model.
I don't see text.
That is a
on your
bad
screen.
color. Yeah, that is a bad color, I think.
Oh, I see. Yeah, the color is.
Yeah, sorry. This should be better. Sorry about that. Is it better? Let me actually switch to this mode. This will be larger. Is it better now?
Yeah, that's better. That's
okay,
better.
good. Okay. So it is electron-phonon interaction is the interaction between electronic modes, which we usually spend a lot of time studying them, the band structure, etc., and the atoms, the underlying atoms that form the lattice. And then we know the phonons are vibrations of these lattices. Now, because both have charges, so electrons have negative charges and atoms have positive charges, when these two obviously can interact. So very generally, I can start writing a coupling term to the Hamiltonian, which is saying that I have a density of electrons at some position in my system, density of atoms, lattice atoms in my system, and they generally will interact with a, let's say, Coulomb interaction. And this is about all the, I integrate over all positions in my system. And when I say a Coulomb interaction, it can be, so in momentum space, I can describe this interaction with, so what I'm writing in the notes is the general thing that usually you should have seen, or you may have seen previously in the solids course, and therefore it is in 3D. But it is easy to just to write it for 2D. It is something that you can do. But I'm going to write everything in 3D, and that means the integrations that I have are in 3D, and also the interaction that I'm writing is in 3D. And I can also have screening that is coming from this function. Now, so this is very general. And one thing that we can say right now about the background positive charge is that we expect the background positive charge to be something uniform with some oscillations. And this is still not going to Jellium model. So far, we haven't, I will say where we are entering the Jellium model. So saying that instead of I have a positive background and some oscillations, and the positive background is going to give me some constant energy that I'm not concerning myself with, and what I need about this in the linear terms is just the oscillations in the positive background. And what the Jellium model will be is about this oscillation in the background charge, saying that it instead of being focused on the atoms and seeing the atoms moving, we will see a uniform, we model the positive background as a uniform charge, a uniform field, and then we can describe this. We're gonna be describing this with a displacement vector d, which is saying that at each moment how I have displaced or distorted my background charges. And obviously you can think about, you can guess that my nothing in my model will depend on d itself and will have to depend on derivatives of d, because if I shift my lattice entirely, which is just adding a term to d, it's not important. And this, then I can describe my phonons in terms of this displacement vector, which is a field that continuous field that I will be working with its derivatives. This is what Jellium model means. At least what I understand from the Jellium model. And now this interaction term that I have here, I can take a Fourier transform of it to write it in terms of entirely in terms of Q. So I said that, okay, this is my interaction V of Q, and then my electron charges, I can write it in terms of my Bloch electrons. Again, I'm not writing a label for here. I have the labels only for momenta and spins, but in general, because I have all the bands, I should have a label for different Bloch bands. For now, I'm thinking about one band. Therefore, I have only K and S. And then the density of electrons, I can write in terms of these operators. Annihilation and creation operators for the electrons. And I will also need a Fourier transform for the displacement vector, for the charge density, or the for the density of atoms. And this part, okay, so I can write this by just definition. It is a Fourier transform of my densities. And now this, the thing here in terms of the displacement field that displacement vector that I defined here in the linear approximation in the Jellium model, the important term will be only divergence of this field, which means that if you have a positive divergence in some point, you will have less background charge there. Therefore, positive divergence with this negative sign will give you a delta n, and what we miss here, obviously, is any shear modes. If we have any shear modes, and we cannot describe it, obviously, we will not get anything here. And this means that at this point, we have lost any information in our description about transverse modes. We can describe our longitudinal phonon modes with this displacement vector and this term that I add, but we will not be able to describe transverse phonons. And it is only the Fourier transform. And what I borrow as background knowledge is how this displacement vector can be written down in terms of phonon annihilations and creations. So it is how we can quantize phonons. So this is textbook stuff, and for just not having enough time, I'm gonna write this down. But so let me finish, and then I will talk more about it. And so there are annihilation and creation terms. So this means that your background charge density will be affected when you create or annihilate a phonon. And moreover, what you can see is that these are only longitudinal phonons because my displacement vector is in the direction that is described by my wave vector. And also what we have here, omega q is my phonon energy. And for q goes to 0, acoustic phonons, this is gonna be proportional to my momentum. This is why phonons are like sound like modes. Therefore, the energy is proportional to q at very small q's. And using this displacement vector and taking the divergence here, we can get the term that we were looking for. Oh, sorry. The minus q just comes from the integration that we have here over position, and therefore gives opposite signs for these terms. And you will see that it is obviously because this comes from the delta functions that come from integration and position. They are related to momentum conservation, as we expect. And let me see if I have any notes to be added about this. Not at the moment. Okay. Okay. Which one is better? Do you see the details in this mode, or should I switch back to the previous one?
Horizontal. It's a little hard to see the.
Okay. Yeah. Okay. Now, putting everything together, what I wanted, now I have, which is an electron-phonon coupling term in momentum space, and so there is interaction term, obviously. And another constant that I didn't introduce. So M and N naught are N naught is the average density that I had. M is the charge of each one of those positive charges. Just not very important. Will not be important to us because at the end, what we do, we will put all the constants and call them deformation potential or whatever. And so this is all the coupling terms, and what they describe is between some electron modes and also phonons. The second one is annihilation. Let me be more clear. Okay, I think now it's better. So the first one, the one that comes from having B and the electron ones. So it is having one electron and one phonon annihilating and then another electron going out. So it is, so this term is gonna be, there is an electron and a phonon going to another electron, and the other term phonon is created, and therefore you can now see that yq and minus q in the annihilation and creation terms is related to the conservation, momentum conservation, because it is having the phonon created or annihilated. And one other important thing for us here will be that now if we think about term that is here, so it is a general coupling term that is proportional, that is function of q, among other things. But if we think about its dependence on q, so we have, what dependences do we have? So we have the dependence on energy here, and we have the dependence on q and also the dielectric function coming from here. But now if we think about q goes to 0. One hand, we said that omega q is proportional to q. And one other thing is that at a small q, we can describe our screening, the dielectric function, with Thomas Fermi screening, which means that epsilon q is proportional to 1 over q squared, which says that the q dependence in the potential, part of it coming from screening, part of it coming from the potential, the Coulomb interaction, will cancel each other and we will not have a q dependence. So all the q dependence that we get at a small q is that g q will be proportional to square root of q. And when you go and calculate any decay rate or any processes, decays for processes that come from this coupling, they will be proportional to g squared, means that the rate or everything for each momentum will be proportional to momentum itself. This is main takeaway for phonons. The phonons, the acoustic phonons with larger momentum will couple strongly, more strongly to the electrons.
I'm having flashbacks to my oral exam prep. This is where the t to the 5th term comes from in the resistivity,
Yeah.
right?
Yeah. Part of it comes from this T. Exactly. So T to the fifth in resistivity, if I remember right, one of the terms, one of the T's comes from this G.
Right.
G squared here.
Right.
Yeah.
Cool.
Oh,
See, I didn't totally forget everything.
I did.
No. Yeah, I'm having PTSD at the moment, but yeah, let's move on.
You didn't even have Levitov as your.
Yeah, I was lucky. That is one of the biggest perks of being in Levitov's group. Okay.
He was challenging.
Yeah, I can guess.
For the YouTube audience, tough but fair.
Okay, now this is the general introduction that I wanted to have, and now let's move on to what I wanted to talk about. Let me again. Okay, good. This is awesome. This is okay. Okay, and I will have one more thing to take care of. This is good. So with this background, what I'm going to talk about is this Purcell-like enhancement. I will say what I mean by Purcell-like, but in general, it is about electron-phonon interactions in long period superlattices, Moiré graphene, for example. And I will let me see whether I am. Okay. After a short review of what this Purcell effect is, and also making a conjecture on what would be its analogous for electron-phonon coupling, I will discuss why twisted bilayer graphene we think is a good platform to study the existence of such an effect, and what are the manifestations of the enhancement that we are talking about. Good. So what is the Purcell effect in photonics? Some background. It's the enhancement of light and matter interaction by spatial confinement. Namely, when we put an atom in a cavity, we get a faster spontaneous photon emission by this atom, by the orbitals of the atom, obviously. So the enhancement is due to the photon mode being confined in the cavity, and hence having a higher density of states. So just very generally, every rate that we have something coupling or interacting with another thing, the rate will be proportional to density of this, and then other the interaction terms. So when we have the confinement for photons, what happens is that there will be a higher density of states. You can just quantify it and show that, oh, you will have this much higher photon emission by the atom because of this higher density of states. Okay. So one can ask, can a similar effect exist for phonon emission by electrons? That is saying, if you replace the atomic states for the electrons by Wannier orbitals of a solid, and instead of photon emission, concern ourselves about the emission of phonons, can we get an enhancement by a more localized confinement? For this, we first need to find a means of confinement, obviously. And one way that is easy in electronics to achieve a confinement is having compact Wannier orbitals. And right now, in the analogy that we made, you can ask that, but this is not an exact analogy, because there we had the photons being confined, but here phonons are not confined in with the Wannier orbitals. And so what am I talking about? But in terms of the density of the states, if you think, is that the localization of electron states here will give us the higher density of states in space, and therefore maybe higher interaction or coupling between electrons and phonons. Therefore, this seems possible to get an enhancement if we have a more compact Wannier orbitals. Therefore, it was interesting enough prediction for us to pursue. The material that we chose for this study, unrelated to any hype in the field, was twisted bilayer graphene. And I think most of you know what twisted bilayer graphene is. We just put 2 layers of graphene on top of each other and get this long period Moiré pattern. And what we have, why do we think that it is good? The property of interest is the flat bands for the magic twist angle. So when we have a twist that is about 1 degree, the magic value, this material hosts very narrow bands that I show here, and these bands are almost horizontal in this band structure plot that I have here. And also the electronic states, Wannier orbitals, sorry, the electronic states of these bands give us well-localized Wannier orbitals in the unit cell. So you can see here that this is my Moiré periodicity, and the Wannier orbital of these flat bands are such that they have very high density in only parts of the unit cell. These localized Wannier orbitals make twisted bilayer graphene a good platform to study the enhancement that can be related to any confinement. And especially because the degree of the localization that gives us the confinement and therefore the enhancement, the degree of this localization is tunable by twist angle. Moreover, high linear in temperature resistivity has already been observed for this material. This usually hints to electron-phonon scattering, but the problem is that the observed values are higher than expected. This mismatch between the values brings up some proposals for exotic scattering mechanisms. There's a long list, but what we ask is that, can we find an alternative explanation? And because we have the enhancement due to localization in mind, maybe that is a good thing to check. So to answer this question and have a closer look at the electron-phonon processes, we develop a model for the material. And it has electron states and in localized Wannier orbitals. So this localized Wannier orbitals, I show with this yellow clouds here. And the important thing about them is that we can now, because we have just a toy model, we can easily tune the localization degree. And it will be with this parameter Kc here. And these electron states coupled to the phonons of underlying short period lattice. So there's a short period lattice in the background, that gives us the phonon models, very similar to two-set bilayer graphene. We have the electronic models effectively in Moiré periodicity, but also we know that the phonon modes are not very distorted. It's not that we don't get flat bands for phonons. We don't get the phonons more or less look like the phonons in the monolayer graphene sheets. We just now have two of them. And then this is the Hamiltonian for the coupling, and now we can guess how this Hamiltonian comes about. And the important thing is that there's a coupling in this Hamiltonian. So I think my next slide is not okay. So we have a coupling that I will tell you where this dependence on Q comes from, but in general, this coupling could be not related to Q. From what we know from graphene is that we will have a coupling proportional only to square root of Q that I have put together with C and H bar here in this term. Therefore, why do I still have some dependence on Q? So this is something new that comes from the localization of my Wannier orbitals. And why is that so? So I will later talk more about this in a more microscopic model. But what you can think is that the localization of the Wannier orbitals in the real space gives me some spread of my Bloch state in the momentum space, where if I have more localized Wannier orbital in the real space, that will translate to more spread Bloch function in the momentum space. I will make this more quantified later, but for now, this is just an intuition to know why, when I have more localized Wannier orbitals, what I get is that my electrons now will couple to more and more phonons. So if you consider just two electronic modes, what happens is that the coupling between them with this phonon can be stronger if the electrons are more compact. And there's one more new feature in this Hamiltonian that I've written here, and this is the sum over G. And where does that come from? This is part of a new feature that we get in two-set bilayer graphene. So we have monolayer graphenes with short period lattice, but then we have a Moiré periodicity that is large period. And you've probably seen this picture of beryllium zones. Sorry, this is not a valid beryllium zone. And you've seen this picture of beryllium zones put on top of each other. Both are hexagonal. And what you get, if you zoom here, is a Moiré beryllium zone, and which is much smaller than underlying monolayer graphene beryllium zones. And what happens is that this happens also for electrons, right? If I go back, so why do I have this many bands for electrons? That is only because my original electron band now has been folded back into this mini beryllium zone that I described. So it is similar to when you go from a diatomic lattice from a monatomic lattice to a diatomic lattice. So you have one mode in the monatomic lattice. When you go to a diatomic lattice, you double your unit cell in real space. You have your beryllium zone in the momentum space, and your mode falls back. And this falling happens also for phonons. So this is what I show here. The phonon modes are also fall. So I started with just one acoustic phonon mode, but now in the mini Brillouin zone, it is just repeated in the mini Brillouin zone. And instead of describing this with the original momentum, which could be original momentum of phonon could be large, I just equivalently write it as a small momentum inside mini Brillouin zone plus a g, and g says that which folding this phonon is coming from. G is a label for the reciprocal lattice vectors. And then what I have, so this having this label naturally helps me, because later what I will do will be separating all phonon, all rates, cooling rates or resistivity due to phonons into different Gs, into different G labels. And I will say that this comes from the normal phonon or Umklapp phonons, first order, second order Umklapp phonons. And from the coupling term here, you can see that what this coupling term does in general is it tunes the coupling for Umklapp phonons. So when I have more localized one, the Umklapp phonons will couple stronger. Go to next. So this is the.
Wait, could I ask a quick question?
Yes.
Go back to the previous slide. One thing I'm wondering is why isn't there I feel like the answer might be trivial, but why is there no sum over G and G prime, where G prime would be for the electron states?
Oh, okay. So that is, I have cheated, and that has gone into sum over bands.
Oh, okay.
Yeah. And then I will only talk about the flat bands, because the remote bands are fully empty or fully occupied.
Thanks.
Sure. And now a little bit of background to see how this enhancement in the coupling comes from the localization, or how, and to give an intuition how it is related to having flat bands. What we do in the continuum model, or let's say I give you a twisted bilayer graphene and ask you what is the band structure. The easiest way to think about it is Bloch theorem, and you say, oh, I know my electron modes in the extended zone, and then I know a coupling between them. And because obviously this coupling is such that breaks the previous periodicity and gives a new Moiré periodicity, therefore, what I will have is that my new Bloch theorem will be that my bands, I should somehow describe all my bands in terms of my previous underlying graphene bands. So what does it say? So these are my electron states that come from original graphene layers, 2 layers. And this, what I have here is not accurate in any terms other than just saying that there is a superposition. And the superposition is that very similar to Bloch theorem. So what do we have in Bloch theorem? That the first thing that you solve is that you have a parabolic band, and then you get some periodicity on top of it. You say V naught cosine of let's say A 2 pi R over A, something like this. Okay, and then what we say is that this state, any state, will be coupled to a state that is in the momentum space, that is separated by a 2 pi over A, right? And what this coupling means is that I have a original state at momentum k naught, but this momentum k naught, now the conservation of momentum is lost, and this momentum k naught is coupled to all k naught plus different g's, and I have a huge matrix that includes all of them, and this means that also on this side all of them, and then I solve it, and the states that I get no longer have a momentum in the extended zone, but they have a momentum label in the beryllium zone and also a band label. But the information that is inside, so this is what we usually get, only the energies, but there is information in the eigenvectors. Information in the eigenvectors is that this Bloch state that I have given you with k and n, what is the composition of this in terms of original momenta that goes beyond mini beryllium zone, and that is the information that I can put inside this, that I will have inside this eigenvector. Similar thing happens when we go from graphene to twisted bilayer graphene. The twisted bilayer graphene gives a periodicity and couples different momenta in the momentum space. In the mini beryllium zone terms, so I choose a momentum, and this will be coupled to, there's a large matrix that, and this will be coupled to all beryllium zones that are, or all momenta that are connected to this momentum with some reciprocal lattice vector. There's a large momentum, I will solve it, I will get these eigenvectors, and these eigenvectors now give me the superposition, give me the composition of this original lattice. And now what I have, now what I have in terms of this original lattice, I know the coupling between different the different electrons with phonons, right? For these sign knots, I know that from the coupling term, for these sign knots, from the electron-phonon coupling term that I had, I know this k will be coupled to k plus q with a momentum q. Now, if I want to write the same coupling term in terms of Bloch states that come from twisted bilayer graphene, because each of these in itself is composed of original graphene Bloch states, it means that now an electron state in K and an electron state in K plus Q are also coupled with a phonon not having momentum Q, but also momentum Q plus G. The strength of this coupling obviously will depend on these composition values that I have here. So it is, if I have a momentum here, obviously it is not very, if I have a state here in its composition, I will not find any contribution from a momentum that is like one valley or the other valley. Therefore, I cannot have a phonon scattering between this state and that state because it will depend on the C that is vanishing. But for smaller distances, this means that I still have these connections. Now, the other thing that if you've worked at continuum model previously or seen it, another thing that happens is that when you get to flat bands, what happens is that this composition is very large in the momentum space. And you need to, for having an accurate band structure calculation, you will need to include up to like 40, 50 different Gs. This means that your Bloch state in the momentum space is very delocalized. This is the same thing as saying in the toy model that the Wannier orbitals are very localized in the momentum space. So this is the connection between having flat bands, on the other hand, having localized Wannier. I'm running out of time, and this is not okay. Localized Wannier, and on the other hand, delocalized Bloch. So all of these are interconnected to each other. Obviously, these two obviously come from just sort of Fourier transform, but you also saw that in the twisted bilayer graphene how achieving flat band means high coupling between different original graphene states, and therefore having very delocalized Bloch and therefore localized Wannier functions. Now, these are the Umklapp processes, and now we have more modes to use to connect to, and the localized Wannier orbital will give us higher enhancement. We can go and do some numerics, and I will this will be what I want to finish with. What we look at is two different things: cooling power and resistivity, coming from Electron-Phonon interaction. Here I show the cooling power for two different Wannier orbital radii. So this is the more localized and less localized ones, and you can see that. So pay attention to the colors. So this is normal, doesn't change much, the lowest band, but the Umklapp ones, these two that are Umklapp ones, you can see that are very different. So we get an enhancement in the first and second Umklapps when we make our Wannier orbital more localized. And there's a similar thing happening for resistivity, say that the normal ones are very similar, but when we make the Wannier orbital localized, the Umklapp ones go higher, and therefore we get larger resistivity. There's a small caveat in the resistivity data, and that is that the enhancement that we had in the cooling is much stronger than in the resistivity. And the reason for it is easy to understand, that the enhancement comes from Umklapps, and in cooling, Umklapps contribute to the process because stronger, because Umklapp phonons have large energy, but the same momentum as the underlying as the normal counterpart. So if you compare in the resistivity, they are relaxing momentum, and Umklapp and normal are the same, but in cooling, they are taking energy out of electrons, and an Umklapp phonon is much better in relaxing energy and getting it out of electronic system. So this is a summary, and I think I went over time, but please ask me questions. But in general, I think I hope at least that it was a nice way of showing that how twisted bilayer graphy and having a confinement of Wannier orbitals can give us enhancement in resistivity and cooling that is coming from phonons. Please ask any questions.
So I'm wondering how much of this is a generic flat band effect.
Yeah, I haven't. So what we haven't done is so the model that we have obviously is not related to TBG, and that is because the title is about long period superlattices. When you have a superlattice, means that you have underlying phonon modes that will give you the bands, and having a flat band will also mean that you will get localized ones because you have the localization in the momentum space. Therefore, this is my understanding is that it should be general. It should be rather general for superlattices with flat bands. What we haven't done is actually calculating it with the double checking it with the microscopic picture for all other systems that have flat bands, like I don't know, TMDs or etc.
So this is. Oh, sorry.
Oh yeah, sorry. I was just gonna say you have looked at the microscopics for graphene TBG specifically.
Yeah. So the numbers that I show here are not microscopics, but we have double checked it with for some values because it is harder to do with microscopics. But we have double checked some of the values with microscopics. Yes.
Okay. Yeah. So this is actually interesting because one of the projects I'm working on currently involves these super lattices. So which is why, but I know Cyprian and you worked on these like plasmon damping mechanisms.
Yes.
At Landau damping, which is 0th order in phonons.
Yeah.
Do you know what the implications of this would have for like 2nd and 3rd order damping of plasmons if these phonon modes are actually highly or well coupled to the electron modes?
So your concern is not Landau damping, but damping of plasmons due to phonons, right?
Yes. Yeah.
And now, even in the 1st order, there should be some contribution. But yeah, in general, people use, I don't know about how much the enhancement. So the enhancement is not, at least the enhancement that we get, is not order of, let's say for the resistivity. It's less than 1 order of magnitude. So it is not something that if previously it is not concerned, so this will not cause it to be concerned. So this is very more like a just quantitative change rather than qualitative change. But qualitatively, people usually ignore phonon decays of phonons or electron-phonon interactions for plasmons, and therefore I don't see that this will change that picture. Okay.
I have other questions if nobody wants.
Yeah, please go. I think you're the.
Yeah, this model that you had of G times e to the minus q squared.
Yes.
Is this in the I saw that you cited your paper at the very beginning. I can. Is it kind of, or is there a good way of understanding that?
It just comes from some. So what we have is what we assume is Gaussian Wannier orbitals.
Okay.
And then what you have, you just Fourier transform. When you have two Bloch states, what you get is Fourier transform of that Gaussian in the real space, and that is also a Gaussian that you see here. And 4 comes from just Gaussian in 2D. That even though we have in the real space we didn't have put 2 in the Gaussian, therefore we get 4 here. That is just how we have labeled them. And yeah, it is easy to get. It is just having a Gaussian Wannier orbital gives you immediately a Gaussian coupling strength in the momentum space.
Okay, I see. And these are you said are these restricted to longitudinal acoustic phonons?
Yes, longitudinal acoustic phonons.
Okay. I guess is it at the temperatures that you're looking at, are the other phonons kind of frozen in, or is it or they're just
so the optical ones are both frozen, and also the energy scale is not irrelevant for flat band dynamics because it is order of magnitude larger, and therefore you cannot decay with a optical phonon. And the transverse phonon, there are also transverse phonons that's usually couple weaker to electrons
Yeah.
because those are only shear modes and not the density modes.
Yeah.
And then, but it's not the full picture. The full picture is that I have two longitudinal phonon modes coming from two layers.
Right.
And because I almost skipped, managed to just not talk about it, is that these two modes obviously will give you two longitudinal modes in Moiré graphene at each momentum, other than this labeling. And one of them is that when two lattices vibrate in the same direction, symmetric, and there's also an anti-symmetric mode. But why the one that I'm talking about is symmetric? Because it is not changing where my Moiré points are. But if you think about the anti-symmetric one, an anti-symmetric distortion, what happens is that it changes your Moiré periodicity. And you can see that by just putting two things that give you the Moiré periodicity. And if you shift one of them slightly, you will see that the Moiré period is shifting much faster. So it is like when you have two veils that you see the Moiré periodicity, if you go right and left, you will see that the periodicity is changing a lot. And the anti-symmetric mode is the same, and it changes your Moiré periodicity a lot. Therefore, but on the other hand, it is not, now it is very distorted. It is not like the original Moiré or original graphene phonons that this has this speed of sound, etc., etc. So they are usually flat, very low energy. So the coupling otherwise, other than the Moiré periodicity, is not that large to electrons. So that is another story. That is a story of another work. Yeah.
Right. Thanks.
Sure.
I have kind of a naive question, I guess, because in superconductivity, I guess like electron-phonon coupling plays a role in BCS, let's say. So
Yeah.
is this in any way, like your story, is it in any way related to anything?
Yes, actually. Yes, actually. If you know Cyprian, he was here and now he's in Caltech. Cyprian has a recent paper. And so what they have is not just superconductivity due to phonons, it is phonons, plasmons, etc., screening. But what they, so it is also very heavily numeric work. But what they have is that let's include these phonons that we are including one by one. Include normal, then Umklapp, then the other Umklapp. And you see that the TC that you get is much higher when you include the Umklapp. So therefore, if there's a phonon plus plasmon mechanism for superconductivity, the Umklapps will have a very high impact on the TC.
When you say include one by one, do you mean like there's like a hierarchy of scales, like you should expect
No. Sorry.
Or
It is just very
just to
in the
compare.
sum. Yeah, just to compare, similar to what we have in here. Yeah.
Cool. Well, if no one has any more questions, thank you, Ali. That was really good. I will attend your March meeting talk. So
thank you. Yeah,
I can
looking
ask
forward to that. Yeah, March meeting. Yeah, I I haven't started thinking about my presentation for March meeting yet, and
yeah,
I just checked the date.
We have
I just
several
checked the date a few days ago, and I was grateful that it's not early in the March and it's mid-March. I said, okay, I have time.
Yeah.
Yeah. Thank you
All
for
right,
listening to my talk. Yeah, it was nice.
cool. And I will see you guys. We'll have a bit of a break, but I'll see you back in April. And I'm scheduling some postdocs to talk. So we have a bit of break time for them.
Awesome. Thanks.
Cool. See you, everyone.